All right, happy Tuesday, week 4. So before we get into today's lesson, I want to talk about the final project that I sent out. So there is a final project folder. It's very important. Hold on a second here. The folder is right, where is it? Okay, it's right here, final project assignment folder. Very, very important. When you click on it and go into it, this is the assignment sheet. It's the same thing I attached to the message. So make sure you are reading that before you submit any pieces to the assignment. So keep looking at it and re-looking at it and re-looking at it. You don't want to miss any pieces of the assignment. So make sure that you're looking at that. I'm going to open up the final project assignment sheet here. So all of the dates are right here, but they're also on the more detailed pieces. Important thing. So the proposal is super informal. Just give me, a sentence or two. Say, hey, I'm really interested in this topic, so I might try this, or, here's an idea I've been mulling around. Give me two or three of them if you need to, and I'm going to give you feedback on everything that you send me. So you can kind of get an idea. This is super, super informal. You don't need to create a Word document. You can just type it into the show work piece and just, throw out some things that you're thinking about, and I'll give you feedback and tell you whether or not I think it's a good idea. Maybe I have some ideas to make it a richer project. It's just kind of whatever pops in my head based on my experience. So the proposal is super informal, and you'll get all 5 points if you send me any idea. So that's for that piece. The data set, there are 3 different pieces. Make sure you read this and that you're submitting all 3 pieces. We need the raw data, 2 variables, 50 data values each. This time it really is 50. It's not 20. It is 50. This is your final project. If you're thinking about doing polls, now's the time to do it for the final project, because it's like a final exam. This is what we use for your final exam. You also need to talk about how was your data obtained. So did you go onto a certain website? Did you ask people? I need to know how you obtained the data. Talk about if there's any kind of bias there. Talk about your sources. Google is not a source. Any of that stuff with how you obtained your data. And then why do you find it interesting? Yes, this time you need to find it interesting. I didn't care with the labs, but I want you to find it interesting. I find that the projects that people really are interested in the topic are generally better. Think about what you want to do after college. Think about what you're training for, what you're in school for. If you pick something that goes along with your future career plans, more than likely it's going to be a better project. I mean, I've had some good projects with things like how much sleep do you get each night versus how much caffeine you consume. I've had some good ones of those, some pretty good ones. But the best projects are the ones where people are, really have strong feelings about what they're talking about. So think about that. Written report. So I have samples of the final project presentation. I do not have samples of the written report, and it's actually kind of intentional, the written report thing. I want the written report to be your own thoughts. Most of the time, it's kind of a stream of consciousness type of a thing where someone says, "Here's the question I'm kind of trying to answer." When I think about that question, I decided this is the 2 variables I needed. So I asked my friends and family. I got those 50, and then I felt like calculating the mean was a good idea. Here's what I was hoping it would show. You're just kind of talking through why you're doing a certain kind of analysis and which type of analysis you did. What did it show you? And just kind of talk through your process. What did you do? What did it show you? What did it lead you to do next? Saying, okay, I got this answer, so I tried this other next thing. Show your graphs. Use Excel to create some great graphs, and you can either paste those into your written report or just keep them on Excel and say, see Excel graph titled this. I'm okay with that. If you submit both your Excel and your written report, you can say, see graph titled this in my Excel sheet. I'm okay with that. And one thing that your written report has to have is one of the formulas has to be hand calculated. So you could type this using the equation editor in Word if you'd like. Some people will write it off on a piece of paper, take a picture and put the picture in. I don't care how you do it, but it has to be hand calculated. I highly recommend using something like a z-score or a mean. Do not try to calculate the correlation coefficient. It is a big pain in the rear. Just don't do it. Make it something simple. Don't overcomplicate it. I don't care what formula you hand calculated. Just give me one. Okay. Any questions before we move on to today's topic? Okay. You're welcome after class on any classes that I'm teaching. You're welcome to throw questions in at the end of class up until obviously it's due. You're more than welcome anytime that something pops up or post it in the discussions. That's probably the best place to put it because your classmates are going to have the same questions and then I could answer it there. That's probably the best place, even though messages are fine as well. Okay, I'm going to close that out. We're going to talk about what we're learning today. Okay. There is no word limit or page limit. Most of the written reports are, if graphs are not included on the written report, it's usually a page and a half to 2 pages. That's usually what it is. There's no upper limit. I mean, I really don't want you to send me a 10-page report. You can, and people have, but I would prefer not to get a 10-page report. But if you have 10 pages worth of good stuff to write, as long as yeah, I go for it. I don't have an upper limit, and it's not technically a lower limit either, but I've never had an A paper that was less than a full page, if that helps you. I've never had a paper thorough enough, less than a full page. Generally, a page and a half to 2 pages, if you don't paste the graphs in, is about right. Pasting the graphs in, it really depends on how many you have, so that I can't really help you there. Slides, generally 8 or 9 slides is usually about normal. And I'm not saying that's what you have to have, but 8 or 9 slides. Look at the examples. The examples are good. All the example projects received passing grades. There's 2 of them that got extra credit, but they all passed. And you can probably, when you look at them, you can probably get an idea of what kind of grades they got. I tried to give a variety. Okay, let's talk about today. So today we're doing chapter 6. Thursday we're doing chapter 7. So our test is going to be on chapters 5, 6, and 7. I know that it feels like, oh, this next test is coming up super quickly, but it is summer term. There's only 8 weeks. We have 2 weeks left, or 2 tests left, and we're in week 4 of 8. So they come quickly, unfortunately. So we do have a test next week. So chapters 5, 6, and 7 are what are going to be on the test. Section 6.2 is where students struggle most in this unit. So hoping I can give you that information well enough for you to grasp it. So 6.1, we are jumping back to quantitative variables. We're going to look at discrete and continuous random variables. There's going to be a lot of stuff that's going to look very familiar, but we're going to learn some really important new stuff here. We're going to look at graphs of discrete probability distributions. That's a really quick blip. We're going to compute and interpret the mean of a discrete random variable. And then we're going to talk about what expected value is and compute the standard deviation of that discrete random variable. So that is 6.1. 6.1 leads us very nicely into 6.2. So 6.2 builds on chapter 5 stuff really well, and it talks about binomial experiments. People, for some reason, really struggle with binomial experiments. I've tried presenting it in many different ways and figuring out where the disconnect is. I haven't quite got there figuring out where that disconnect is, but I will make sure I'm very much available to answer questions because it seems to be a problem. We're going to compute probabilities of binomial experiments. We're going to do mean and standard deviation, and then we're going to look at the graph. The graph, once again, is super fast. So this is our chapter 6. This is what we're doing today, and I'm going to jump into it. My iPad will turn back on. All right. So for random variables, we use a capital letter X. I don't know why whenever they choose to use a capital and a lowercase letter for different things, they choose letters that don't look different when they're capital or lowercase. It just is what it is. I don't care if your capitals look like capitals and your lowercase, I don't care. If you put an X there, I'm going to just trust you. So a random variable is the numerical measure of the outcome of an experiment. So I'm trying to think of a good one, and I can't think of one. I have examples that are in our lesson, and you'll get one. You'll understand what I'm talking about. So random variables are basically you have a lot of different numerical values that can come out of an experiment, and then you're going to have different probabilities of each outcome. So I guess rolling dice, we have that. We could get 1, 2, 3, 4, 5, or 6 rolling a dice, and each of those is going to have the same probability. But if I'm rolling 2 dice, I'm going to have a different probability for rolling a 2 than for rolling a 7. So we would list all the possible outcomes, and then you'd have the probability of each outcome next to it. And that's what we're going to be working with here. I'll show you. So let's talk about discrete and continuous. We did these previously, but these kind of come back up again. So discrete has a finite or countable number of values. So if I was graphing them, I lift the pencil with each one. So I'd have to lift my pencil to graph it. It'd be dots. If it was on a coordinate grid, I hate when that happens. If it was on a coordinate grid, it would look like this. It would just be dots. Continuous has infinitely many values, so all of the ones in between. If it was on a coordinate grid, I would not lift my pencil to graph it. So we did these before, discrete and continuous random variables, basically the same meaning that discrete and continuous had previously in like chapter 1 or whatever that was way back in the beginning. Okay. So let's just quickly go through these, and I'm trying to the stuff that is review, I'm rushing through it a little bit so I can linger on the stuff that's not review. So we're going to talk about whether they're discrete or continuous. So the number of light bulbs that burn out in a room of 10 light bulbs, I'm not going to have 3.5 light bulbs burn out. I might have 3 light bulbs burn out. So this would be discrete. Right, good. The number of leaves on a randomly selected oak tree. Though I don't like counting them, you're most likely not gonna lose 1 7/8 of a leaf. You're going to lose 1 leaf, 2 leaves, 1,000 leaves. So this would also be discrete. The length of time between 911 calls. I have to wait 2 minutes and 36 seconds before I can wait 2 minutes and 37 seconds and 2 minutes 36.8 seconds. It has to go through all of the times leading up to the time when the phone finally rings. So it can take on any value in between the minutes. Therefore, this would be continuous. Make sense? Are we good? Okay. All right. We learned, I believe it was last week about last week, was it? I think it was before that. About probability distributions. I actually think it was, when was that? I don't know. We talked about them. So a probability distribution, this was actually last week. It was 5.3. It can be in that we use tables, graphs, or mathematical formulas. So probability distributions are where we have all of the outcomes and the list of the probabilities. We did them with categorical variables within our probability unit in section 5.3. Remember when we were learning the complement rule, we used it, and we used it for the housing, and I believe there were other things also. But so probability distribution, once again, all of the probabilities are going to add up to 1, and all probabilities are between 0 and 1, because I can't have 113% chance of something happening. So it has to be between 0 and 1. So with our probability distribution here, we'll have all of the possible values in one column and then the probability of them occurring in the other column. So here we have it right here. So this is the number of movies streamed each month on Netflix. So my X value here is all of the possible outcomes. I guess people aren't streaming more than 5 movies on Netflix in a month, but at least not in this group, whoever was polled. So they polled a whole bunch of people and asked them, or maybe they looked at Netflix's data. I don't know how they did it, but they looked at the number of movies that they streamed on Netflix each month and have all the probabilities here. So if I randomly selected a person who watches Netflix, there's a 58% chance that they watched one movie, streamed one movie on Netflix this month, if that makes sense. So we have our outcome and then the probability of that outcome. Okay, so this is a probability distribution. If I added all these up, I would get 100%. Just trust me on that. And they're all between 0 and 1. Okay, see, here it is right here. This right here, this just means add them all up, or the sum of. The sum of all the probabilities equals 1, and each probability is between 0 and 1. See, I knew I had that written somewhere. I guess it was just not 5.3, it was in 6.1. You teach this enough, you just forget which section it's in. Like I know I have it. Just don't remember where. Okay. So probability histograms are going to look exactly like a relative frequency histogram. Exactly. They're the same thing. We just replaced the words relative frequency with probability. It's exactly the same thing. It's even calculated the same way. So we just replace relative frequency with probability, and it's going to look the same. So I'm going to show you the one here. So here we go. So notice how we have our number of movies streamed is on the horizontal axis. My vertical axis is the probability. So I just took that probability distribution and just made a nice histogram there. I'm going to show you a lazy one later. That is not one that you would use for displaying your data in an office meeting, but it's a like real quick way to show yourself so you can kind of see, is it skewed or whatever. Like right here, I'm sure you can look at this and see that we have basically a right skew right here. My histogram is right skewed. It's not as noticeable in the table. So sometimes throwing it into a histogram helps us a little bit to see the shape of our distribution. So I'm going to show you the lazy man's way in a minute. I hope it's okay that I'm kind of moving right along. None of this is super new yet. So once I get to the new stuff, I'm going to slow way down. All right. So suppose we took a basketball player and we wanted him to shoot 3 free throws a whole bunch of times. So we just had him over and over and over again trying to shoot 3 free throws. Say 3 free throws 10 times fast. It's not easy. Okay. So here is based on the outcome of this person. This is our probability distribution. If you randomly had him throw 3 free throws, the probability of him making 2 of them is 38%. It's hard to say 3 free throws. It's hard. All right. I'm going to show you the histogram. This is the lazy man's histogram. It is lazy. It is not something you're going to display for if you're in a meeting and you're sharing your data with with the president of the company or whatever, this is not the histogram you're going to show him. But this is the lazy man's histogram. So you can kind of just see the shape of your distribution. You can just kind of get an idea of what it's going to look like. This is without making it super pretty. You just draw it real quick. I just put a dot there. Whoa. I just put a dot there and then just drew a line up, whoa, to that probability. That's all I did. And this absolutely okay for what during your work when you're just working through something. So I can say, oh, well, this is clearly left skewed. If you're just kind of working through something to kind of get an idea of what it's going to look like, this is absolutely okay. But when you put your presentation together for your boss, you're going to give him this histogram. That makes sense. So this is a lazy man's histogram. Okay, now's when I'm going to slow down. So expected value or mean, the mean of a discrete random variable. Because each of these has a different probability, I can't just add all of these values together and divide by how many they are, because each one has a different probability of happening. So what I have to do instead is I have to have a different way of calculating that mean. So what you do is you take each data value, you multiply it by the probability, and then we're going to add them all together. So here's what it's going to look like. 0 times 0.06. Yes, I know that's just 0, but just for consistency, I always just include the 0. 1 times 0.58 plus 2 times 0.22 plus 3 times 0.10, 4 times 0.03, 5 times 0.01. You can put the whole thing in your calculator at one time and just take each data value, multiply by the probabilities, and just add them together. So I'm just going to do that right here. My calculator's doing weird things. Plus 1 times 0.58 plus 2 times 0.22 plus 3, 0.10 plus 4 times 0. That's a 1. That's not a 4. 4 times 0.03 plus 5 times 0.01. So I got 1.49. The symbol that we use is mu sub x, because that's a subscript. So it's mu sub x. So this is saying this is the mean of a random variable x. Technically, that's supposed to be a capital X, but I don't care. You can't tell, right? You can't tell one way or the other unless I compared it with another x. Technically, it's a capital X. So mu sub x would be approximately 1.49. So what this is telling me is that if I had a whole bunch of people, so I took, I don't even know a number. Let's say I took 2,000 people and I took all of the number of movies that they watched. Asked 2,000 people how many movies they watched on Netflix, how many they watched per month, and I averaged all of those answers together, I should get 1.49. That is the average of everybody's viewing habits based on this probability model. It's called the law of large numbers. I believe I have a graph. I will later. So that's called the law of large numbers, that when the larger the sample size, the closer you're going to get to this mean, the closer you're going to get to this value right here. So the larger our sample size, and I'm not going to ask you to reiterate that it's the law of large numbers, but that's what it's called. It's not a fancy, we don't get a fancy name. All right. Questions so far? We get so far? So this mean that we just calculated, and actually I pretty much just said this. As the number of repetitions of the experiment increases, the mean value will approach mu sub x. That's basically what I just said. As we get more and more and more samples, as we have more and more people that we ask, how many movies do you watch per month? Our average is going to get closer to that mean. That's what that means. That's the interpretation. Okay. Questions, comments, queries, concerns? All righty. We're not at complicated stuff. There's the picture. So this was, remember I said that as we pick more and more and more samples, we're going to get closer to that. This is 100 trials. So we're down here, we're kind of all over the place. Taking the average, it's kind of all over the place. But as we get more and more and more, notice how this is trending up here. As I get more and more, what I'm doing is averaging it as I go along. Add another one in and average it. Add another one in and average it, and just keeping it going. So our average is going to approach that number. That's what that lovely picture is. Okay. So this mean that we just calculated, we call it the expected value. So it is what we just calculated. Yes, it's the mean of the discrete random variable, but we call it the expected value because it's what we would expect if we do a large number of trials. It is the value we expect to see. We would expect if I did a whole lot of trials of asking people how many Netflix movies did you watch, we would expect that average to approach the 1.49. It is the expected value. Expected value is used a lot in like casino games. So what the casino wants it to be that for every dollar spent, that they spent by the consumers, that they would expect that they would make slightly more than that the consumers might get back 98 cents. The consumers might get back 97 cents, so that the casino ends up making, I don't know, 3 or 4 cents off of every dollar. They want it to be really close, because if people aren't getting back really close to what they paid in, they're not going to keep playing the games. So the casinos on purpose make it so that the expected value for the consumer of every dollar that they put in is close to the dollar, but not quite there. So, because if the casino is making 3 or 4 cents on every dollar, that's going to add up. They're going to end up with a lot of money. So expected value is really big on that. And we're going to have a life insurance example in a few minutes that shows you how important that expected value is. All right. This is it right here, as a matter of fact. Look at that. So a term life insurance policy pays a beneficiary money if they die, or upon the death of the policyholder, a beneficiary makes money. So people pay premiums. So this one right here has an annual premium of $530 for a 49-year-old female. If she dies within that year, it pays out $250,000. Her survival rate is 0.99791. So what we want to know is how much money, with the law of large numbers, and some of these people are going to die. If they have a ton of these policies, some of them are going to die. So we want to know how much money is the insurance company expecting to make off of each policy. So let's take a look. So I know that if the person survives, the insurance company made $530. They made $530 if the person survives. That 49-year-old female survives, the insurance company made $530. If she does not survive, the insurance company loses $249,470 because she paid in $530. So I have to subtract that from the 250, or subtract the 250 from it. So they lose $249,470. The probability of them paying that out is this right here. It's really small. So what we're trying to do is calculate how much, with all of these policies, how much the insurance company expects to make per policy. So we take the $530 times 0.99791. plus, I don't like writing it this way, negative 249, 470 times the 0.00209. This will tell us what they expect to make. So I'm going to put this in my calculator. The insurance company is expecting to make $7.50 per policy. Now that doesn't seem like a lot. I sure hope that's the number was over here. Yeah. It doesn't seem like a lot, but think about it. If they have thousands of these policies sold, they're making some money. They're making bank. And there is a person. Oh, my screen sharing is slowing down. Okay, thank you. Yeah, I wish it sometimes the heat or whatever, it just lags. Okay. So they I just lost my train of thought. They they want to keep the policies as low as they can, but still make money. So 750 may not seem like much per policy, but if they're selling thousands of them, they're making a lot of money. So there's a person who sits in a room called an actuary and does these types of calculations. They do this type of work to calculate these probabilities so that the insurance companies can make money but still keep the rates low. And they do this with things like car seat safety. They do this like things with like car accidents and seat belts and all of this. They take all of this stuff into consideration. Actuaries sit there and calculate these probabilities and these expected values for insurance companies. That's their job. And they make really good money. If you're really good at statistics, you can get a degree in statistics and become an actuary and make some really good money. I considered it for a minute, but I'm not a cubicle kind of girl, so I didn't continue. All right, questions before we move on? All right. Okay. I'm going to go back to the Netflix example. We already did the expected value, so I'm going to move on. My expected value was that $1.49 or that 1.49. That was the expected value. Let's do let's calculate the free throw shooting. I would like you to do this, and I'm going to work slowly behind you. Go ahead and calculate your expected value, how many hoops we would expect them to make, if they did what the average would be if they did this a whole lot of times. So go ahead and start. I'll work slowly behind you, especially since there's a delay. It's perfect. I did something wrong. Oh, yes, good. 2.39. So if he repeated these trials over and over and over and over and over again, we would expect him to average about 2.39 free throws out of three. This is a good basketball player. So I would be averaging really close to zero, really close. I'm also short, but short people can play basketball too. I'm just not good at it. So I'm going to show you how to calculate the expected value on your calculator, because sometimes you're going to have a large data set. So I'm going to show you how to do this on your calculator. We're going to do the Netflix data. I'm going to jump back to this page and we're going to do calculator. So grab your fancy schmancy. Okay. We're going to click on the stat button and we're going to go edit. We want to be in our lists. In the L1, you're going to put the outcomes. So 0, enter 1. So you're going to put the values of your random variable. That's going to be in your L1. L2 is going to put, you're going to put the corresponding probabilities. And after you're done, make sure you peek up there and make sure you have the right ones in there because I'm the typo queen. So I always have to make sure that I type them in correctly. Give you a second. All right. So now, once again, we're going to run our 1 bar stats, but we're going to do it just slightly different. Okay. Click on stat, arrow over to calc. We want 1 variable statistics. We want that first option. Our list is L1, but our frequency list, that's what freq list means, frequency list. You're going to put L2. So where we put the probabilities, so it's second 2 gives you L2. In your frequency list, you're putting L2. This is going to tell it to multiply it by that. So once again, your list is L1, your frequency list is L2. If you forgot how to put that in, do second 2. That gives us the L2, and then go ahead and hit calculate. 1.49 is exactly what we got using our calculator, right? There we go. Now we're ignoring all the rest of it. None of the rest of this is meaningful. So we're ignoring everything else. But right now we're just looking at that X bar. That is our expected value. That X bar is the expected value. And that's it. So it's not super complicated. Okay. And you absolutely can just do this with your homework. You don't have to do it by hand. Absolutely use your calculator. This is why we have it. Why not use the tools that we have? Okay, I'm popping back over. We're going to talk about standard deviation. Now, I don't want you calculating this by hand, but I'm going to tell you how to do it. But we're not going to be calculating it by hand. We're going to use the calculator. Standard deviation, it's so easy to make mistakes here, but I'm going to tell you how to do it. So I would take each data value minus the expected value, then square it and multiply it by the probability. You do that with each data value, and then you're going to add them all together. So take data value minus the expected value, square it, multiply it by the probability, and then add them all together. That's how we calculate that. We are not going to do it by hand. I used to teach it doing it by hand, but it just is the making mistakes is way too easy. And as I said, you have the tools, use them. So let's do with this is the free throw data. So I'm going to go back to my calculator, go back to my stat, edit. I'm going to do, don't erase these. Let's go to list 3. We're going to do 3 and 4. I do this all the time when I'm jumping back and forth between data sets. Let's do list 3. I'm going to do the free throws. So 0, 1, 2, 3. And let's put the probabilities in there and 4. List 4 is where we're going to put the probabilities. And then take a look at them, make sure that you have them correct. when we do one var stats, we're going to use list 3 and list 4 because that's where I have these. We're going to do list 3 and list 4. So do stat, arrow over to calc, one variable statistics. So my list is second 3. That gives me list 3. My frequency list is second 4. That gives me L4. Now, if you did 1 and 2 instead, it doesn't matter. Just wherever your list is, wherever your data values are, that's your list. Wherever the probabilities are, that's your frequency list. And hit calculate. This is the same expected value that we had. Notice how there's no SX. That's okay. It's because we don't do sample standard deviation with expected value. We just don't. So all we have is the population standard deviation. So my standard deviation here, I'm going to write these down. Hold on here. I'm just going to write it on my, I'll do 706. So our standard deviation is right there. And the meanings are the same. The meaning is the same when we're looking for outliers. And we don't use the standard deviation a lot. We seriously don't. If you want the variance, you just square this, because back here I forgot to show you. You take the square root. Just a second, it'll go back to that screen. Back here, I forgot to show you. You take the square root at the end. I think you guys probably saw that. But the variance is just squared of the standard deviation, which we never use it for anything. It is basically meaningless. So it would be 0.498. All I did was squared. If I just took 0.706 and squared it, there is no variance on here. But you just square the standard deviation to get the variance. But I've never used the variance for anything. So this is what it is. I have questions before we move on. Okay. So my expected value was 2.39. We already had that. Standard deviation 0.706. And my variance is 0.498. So I just put a squared on my standard deviation. So we just do sigma sub x. That tells us that this is the standard deviation of the random variable. Okay. We already did this, except for I'm going to show you where we didn't actually do the standard deviation. I'm just going to go back. This is why I kept those in there. Go to calc, one var stats once again, second L1, because I left them in there, second L2. So why I left them in the calculator. So we already have our expected value here, right, is my standard deviation right here. So my sigma sub x, 0.933 approximately. And if I squared that number, I'd get the variance. I can't remember if the homework does asks for the variance or not. I can't remember. When I squared it, I got 0.870. And I almost never use the standard deviation with expected value, just if the assignment tells us to. I'm going to tell you that on the test, you will not have to find the standard deviation of the expected value. You will not. The homework might ask for it. You're not going to have to do that on the test. I will probably ask you for an expected value of something and maybe ask you to interpret it. If you interpret it, all I want you to say is that if there were a large number of trials, we would expect the average to be this. That's all I'm asking for you. Say if there were a large number of trials, I would expect I'd expect the mean to be 1.49 or whatever. The average number of movies people watch to be 1.49. So I want you to say large number of trials, or you can say according to the law of large numbers. All right, questions before I move on, because I think we're at 6.2 after this. Questions on 6.1. Okay, 6.2 is where you're going to need to use a little bit more brain power. This is where people get confused. Usually 6.1, people are like, oh yeah, that's not bad at all. I'm good. This is fine. 6.2 is where things get a little bit more complicated, and I don't know an easier way to teach it. So we're just going to jump into the deep end and we're going to be fine, right? Okay. Binomial probability distributions. So first thing we need to know is we need to know if it is a binomial experiment. So these are the things that we're going to look for to determine if something is a binomial experiment. I don't believe the homework asks you if something is binomial experiment. I don't make you on the test tell me, is it a binomial experiment? But it is, if you're going to use this in real life, which I do, but then again, I am a math teacher, so kind of everything causes me to be like, oh, yay, I get to use that fun tool I know. I, that happens a lot where sometimes I'll just math it out just because it's fun. I've actually used binomial probability experiments to prove that kids are cheating, which is kind of fun. Yeah, so I had a student that got out of 25 questions, she only missed one question. And she told me, I had no idea on any of them. I just randomly chose every single one. And she got all but one correct, or all but one wrong. No, all but one correct. Yeah. So she only missed one. And I was like, that is impossible. She's like, no, no, seriously, I guessed on all of them and I only got one wrong. And so I calculated the probability of actually getting that many correct by just guessing. And the probability was like a millionth of 1% or something. It was something so small that there was no chance. And I'm like, see, math shows that you didn't actually do that. So yeah, you cheated. And I actually used that data to go to my principal when he called her parents. So he was able to say, yeah, this is what happened. So it's fun math. All right. So here's what needs to be true for this to be a binomial experiment. We have to have a fixed number of trials. So we would have to say something like, I guessed on 25 questions, or he shot 3 free throws, or whatever. There needs to be a fixed number of trials. The trials have to be independent, so the outcome of one trial can't affect the outcome of another. So flipping coins or pulling card out of a deck, but then putting it back in there, shuffling it again. So each one has to be independent. We already talked about independence with our probability. We did that in 5.3. Every trial, there needs to be two mutually exclusive outcomes. It's a success or failure. So rolling a dice, yes, there's 6 outcomes, but if I'm looking for rolling the number 3, I either have a 3 or not a 3. So those are two different outcomes. So we have a success or a failure. And the probability of success has to be fixed for each trial. So my probability is not going to change for each trial. So these are the 4 things we have to have for a binomial probability experiment. All right. So let's take a look at some. We're going to do some examples here in a minute, but look at the notation first. This notation is kind of important because the formula that I give you is going to use these letters. So the lowercase n is the number of trials. We actually are going to use these same notation like throughout the rest of our class. So it's good to kind of get these down. A lowercase n is the number of trials, and we're always going to use a lowercase n for how many trials we have. How many times did we repeat the experiment? So a lowercase p is the probability of success. So 1 minus p is the probability of failure. So P is probability of success, 1 minus P, or the complement of P is our probability of failure. So capital X or lowercase x, I don't care which one you use, but this is going to be our random variable. This is the number of successes. So our X is going to be how many successes we have or how many successes we're looking for. So this is our notation here. Our number of successes has to be between 0 and how many trials we have. If I have 35 questions on a test, I'm not going to get 38 of them right. It has to be between 0 and 35. So these are the things, the notation that we're going to use today. Okay. Are we good? Okay. So we're going to take a look at these and find out if they're binomial experiments and why they aren't if they're not. So a player rolls a pair of fair dice 10 times. The number X of sevens is recorded. Okay. Uh-oh. So is it a fixed number of trials? Yes. He rolled it 10 times. So what's the next thing we're looking for? Are the trials independent? Yeah, because every time I roll the dice, it's going to be different, right? And our success is rolling a 7. So since our success is rolling a 7, then that's our probability of success is fixed. There's two mutually exclusives. I either rolled a 7 or I didn't roll a 7. So yes, binomial. Yes, binomial. Okay, let's take a look at the next one. The 11 largest airlines, I thought I had this like the answers. Nope. Okay. The 11 largest airlines had an on-time percentage of 84.7%. In November 2001, whatever these people, they decided to assess the reason for delays. So they randomly selected flights until they found 10 that were not on time. So first thing was a fixed number of trials. We do not have a fixed number of trials. Right, exactly. It's no, because there's not a fixed number of trials because they keep pulling flights until they got 10 that were not on time. So technically, this is called a geometric probability, but you're not going to learn that unless you take 247 or yeah. So don't even worry, or 244. So don't even worry about it. I don't think any of you are taking 244, which is the next stats class. So this is not a binomial probability, so we can't use the math in this section for this because it's not a binomial experiment. We would just say we can't use the math for this and move on. All the rest is there. There's a fixed number probability of success right there. And technically, though, you almost could say that they're not independent. They might be independent, but the planes could affect each other. I would almost say that they're not independent because the flights could affect each other, right? If something is taxiing on the runway, taking 10 out would be fixed number. So if I only looked at 10 flights, yes, it'd be fixed. So if I took like the first 10 flights and calculated how many were on time, that would be a fixed number, yes. All right, let's look at the next one. In a class of 30 students, 55% are female. The instructor randomly selects 4 students. The number X of females selected is recorded. Okay. Fixed number of trials. Yeah, he took 4 students. Are there 2 mutually exclusive outcomes? There are. They could either be a female or not a female. See, this is see, you have your little question mark there. That question mark was right. Once I take 1 student out of the class, doesn't the probability change? Because now there's only 29 students in the class. And so if I took a female out, then there's 1 fewer female in the class of 29. If I took a male out, then I have 1 less male. So this is not, the probability is not fixed. So this is not binomial. Probability not fixed. I guess I should have written it on the last one, but. Because after I take out the first student, now I'm looking at 29 students in the class. Then I take out another one. Now there's 28 that I'm drawing from. So the probability won't be fixed. I know that one was kind of tricky. Okay.
I'd like to ask you something,
Yes.
please. So
Yes.
how do you, so how do you know if someone's going to take one out or not? Like when you look at that,
Mhm.
who's running just in general, if it's possible that someone could decide to take one out.
Okay,
Is that it? Because
okay,
that's where I
he
feel
randomly selected four students out of a class of 30, okay? So let's say because he's going to take out one at a time, all right? So when he takes one student out, let's say here's my 30 students, this is my 30. He takes one student out, it's a female, okay? So 55, I'm going to say what 50, uh-oh, cancel.
Mhm.
0.55 times 30. So at 16 and a half females, well, that's weird. Let's say there were 17 females in there. Okay. Now, out of 29 students, I have, there were 17 females. Now I have 16 females in there. So 16 divided by
Oh,
55. Yes. So see?
I do see now.
Yes. And so
Yeah.
if I took another one out, let's say I took another female out. Now I have 28 students in there, and there's 15 that are female. So
Okay.
now that probability is changing with every one that's taken out.
I get it now. I didn't before, but thank you.
Yes. Yeah, and you're right. So that's the thing is with the flights, I it's like I'm hesitant to say that it's independent. And I guess if it's randomly selecting flights from the whole world, and maybe that's what they're doing, maybe they're randomly selecting flights from the whole world, then those would be independent. Like say I randomly selected 10 from the whole world, then that would be independent. But if I'm taking 10 flights from the same airport, then those would not be independent. Does that make sense? Does that help? Okay. Yeah, it's kind of sometimes it's kind of splitting hairs. You just have to use your best guess. We don't deal in absolutes. So you just kind of say, it's not likely they're affecting each other, so we're just going to call it independent. But this one clearly the probability changes. This one right here, you have to think, is it the same airport or is it the whole world? Okay. Um, let's talk about our probability distribution here. So according to, and this is, I'm going to show you the tree diagram. I'm not going to ask you to make a tree diagram, but this is kind of give you an idea of different outcomes. And this is going to lead into our fun calculator function that we're going to learn today. So according to the Red Cross, 7% of people in the United States have type O negative blood. A simple random sample of size 4 is obtained, and the number of people with type O negative is recorded. And we're going to construct a probability distribution. So we have a simple random sample of size 4. That is our trial size. We have 4 trials, a trial of size of 4. So our N is 4. That means that's the first thing we need. We're assuming that it's independent because it's people out of the whole United States. We took 4 people. Those are independent trials. The probability stays the same because that's a whole lot of people. It's 7% of people. That stays the same. There's 2 possible outcomes. They're either O negative or not O negative. We have a binomial distribution here. All right. So this is going to be really ugly and huge, and you're going to be thankful I don't make you draw one. Okay. So our first trial is we took a person. That was either a success or a failure. It was either type O negative or not type O negative. My second trial, so I'm going to go on the success one here. So if my first trial I got a success, my second trial I either have a success or a failure. So let's say we got another success. So off of that one, my third trial, I either got a success or a failure. Let's say I got a failure this time. So the fourth trial, I either had a success or a failure. Let's say I have a failure again. So they either were type O or not. So here I had success, success, failure, failure. So in this case, out of my 4, I had 2 successes and 2 failures. So out of the four, these are all of the possibilities though. I could have success, 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 success. I could have failure, 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 failure. I could have any combination here. But these over here shows you how this works. Hold on a second here. So these are all the different ways that I can get successes and failures. I could have all four successes. I could have three successes in a row, then a failure. I could have two successes, then a failure, then a success. So remember when we were talking about flipping coins, I could have heads, tails, or I could have tails, heads. Those are two different things. Or rolling two dice. 3, 4 is different than 4, 3. So if you look at this, I have one, two, I have one, two, three, four different ways to get three successes. Oops. I have one, two, three, four, five, six different ways to get two successes. So I have all of these different ways to get successes and failures. So this would be a whole lot of math if I'm trying to figure out the probability of getting three successes. And I'm going to do the math in a minute, but we would use our and probability. We would do the and probability because you'd say success and success and success and success, or success and failure and success and success. And you'd have to do this with how many ways there are to get those successes. So I'm going to show you the math, and then I'm going to show you an easier way to do the math with your calculator. So let's start here. So we had one way to get 0 successes. So this is the easy one. One way to get 0 successes. So we have 4 failures. So we had a 93% chance of getting a failure. And since this is an and probability, we're multiplying them. So 93 times 93 times 93 times 93. We have almost basically about 75% chance of getting 0 successes. So that's right here in my probability distribution table. So we had 4 different ways of getting 1 success. 4 different ways. So we have failure to the third power because it's 3 failures, and success once. So failure to the third power times success, and there's 4 different ways to do that. So I'm going to multiply that by 4. So our probability of getting 3 successes is about 22.5%. So 2 successes, we have 6 different ways to get 2 successes. So we have 0.93 squared because that's 2 successes. And if we have 2 successes, or that was 2 failures, sorry. 0.07 squared because we have 2 successes. We have 2 successes and 2 failures. And there's 6 different ways. So we multiply it by 6. So it's about 2.5%. And we do this with 3 and we do this with 4. That's a whole lot of math. You guys do not want to build your probability distribution like this, right? What if it was something with like 8 different outcomes? You do not want to build your table like this. Thank goodness we have our fancy schmancy calculators. Thank goodness we have a way to do this on our calculator without going through all of this. There is a way using combinatorics. I don't know if you guys remember a long, long time ago from high school with combinations and permutations. I don't even know if your high school taught combinations and permutations. That is one way to do it, but we're going to use a specific function in our calculator that is less confusing. Okay. This is the way to do it with combinations and permutations. I'm not even going to go into it. We're going to just ignore this. I'm going to just draw a circle around it. Apparently, I'm going to go like this. We're not going to learn that. Instead, we're going to learn this right here. Okay, so I'm going to, don't worry, I'm going to show you on the calculator. It's binom PDF. So what PDF stands for is probability distribution function. You don't have to memorize that. Binomial probability distribution function. This right here is the number of trials. This is probability of success. And this is number of successes. So number of trials, probability of success, and number of successes. So that's what we're going to be putting into our calculator. I'll show you how to get there. I'll show you 3 times, 4 times, however many times you need to get there, I will show you. But once we use this, when we use binom PDF, we can look at the probability of getting an exact number of successes. I'm going to move on to the next page. All right. According to Experian Automotive, 35% of all car-owning households have 3 or more cars. In a random sample of 20 car-owning households, what's the probability that exactly 5 have 3 or more cars? Let me show you what this looks like. When I put it in my calculator, what I'm looking for is the probability x equals 5. That's what I'm looking for. The probability that my random variable equals 5. This is going to look like the setup, binom PDF. So first thing we look at is number of trials, 20 car owning households. Probability of success, 0.35. Number of successes we want exactly 5. So this is what it's going to look like in my calculator. Hopefully you have the pretty screen that I do. If not, when you put it in like this, it's going to work. Okay, let me jump over to the calculator. Okay, clear this out. All right, the way that we get there. So notice this button right here that says VARs. Above VARs, it says DISTR. This is distributions. We're looking at a probability distribution. So that's why we want this distribution button. So I'm going to hit second, and then VARs. That gets me to the distributions. Then scroll down, keep going down to A right there. Binom PDF. That's what we're looking for. Binom PDF. I'm going to clear this out and go there again. Second to VARs. Scroll down to binom PDF and hit enter. I get this lovely screen. I don't know if you get this lovely screen. If you don't, that's fine, because you can just put the numbers in the way that I showed on that screen. The way you can put the numbers in like this. Okay. The number of trials is there are 20 trials. Probability 0.35. Make sure you're converting it to a decimal. And then X value, that's how many successes we're looking for. I'm looking for 5. 20 trials, probability 0.35. So this is saying if I did 20 trials with a 35% probability, what's the probability exactly 5 are successes? This is what it'll look like if you don't have that fancy screen that I have. You put it in like this, and I'm going to hit enter. So that probability, 0.127. So if I took 20 car owning households, the probability that exactly 5 of them will have 3 or more cars is about 12.7%. Questions? We're going to do another one. All right. I'm going to add something though before we do it. Don't worry, we're going to put it all together, but I'm going to add little pieces here, and then we're going to put it all together. Oh wait, this is exactly what I just did. Okay. So a lot of times we don't want to know how many when exactly 5. Sometimes we want to know something like less than 4, or sometimes we want to know between 5 and 7 or greater than 8 or whatever. We want to know a range of values. So we just use binom PDF. We just use that. That was for exact. We have another function when we want a range of values. So notice here we have less than 4. So I want to know the probability that my X value is less than 4. We have another function, binom CDF. And I'm going to put the NPX. So the C stands for cumulative. So remember what that cumulative means, like adding them all up, right? So the cumulative function gives us less than or equal to. I'm going to write it down. Less than or equal to. So if we want the probability that less than 4, we need to look at less than or equal to 3, because 4 is not part of our solution, because less than 4 means either 0, 1, 2, or 3, right? So this is the same thing as the probability that X is less than or equal to 3, because less than 4 is the same thing as less than or equal to 3. So if I'm looking for the probability that less than 4 have 3 or more cars, I need the probability that less than or equal to 3. So what this is going to look like, my number of trials is still 20. My probability is 0.35. My number of successes is going to be 3 or fewer. So remember that CDF stands for cumulative distribution function. PDF is probably just a probability distribution function. The way that I remember it, PDF, P for precise, CDF, C for cumulative. That's how I remember it. That's the only way that I can get it into my brain. I'm going to pop back over to my calculator. Okay. So once again, you do second vars because we're going to the distributions. I'm going down to it's right below PDF is CDF. So CDF is cumulative, PDF is precise, so we want cumulative. Number of trials is 20. Probability 0.35. And we're doing 3 or fewer for my X value. So if you don't have the fancy screen that I have, it'll look like this when you put it in your calculator. I'm going to hit enter. Approximately 0.044. So we only have about a 4.4% chance that 3 or fewer. Questions on this? Okay. We're going to kind of bring it all together, unless you have a question before we move on. Okay. Okay. So we're going to do an at least. I know I said this about 20 times on Thursday. Every time you see the words at least, you use the complement rule. Every time you see the words at least, use the complement rule. This does not change no matter what we're learning around here. Every time you see the words at least, we're going to use the complement rule. So, in a random sample of 20 car-owning households, what's the probability at least 4 have 3 or more cars? So what we're looking for, the probability that our X is greater than or equal to 4, correct? So it'd be 4, 5, 6, 7, 8, and all the way up to 20. I'm going to kind of draw a little picture here. It's going to be really ugly. I mean, it's numbers, but so in our trial, we could have 0 successes, 1 success, 2 successes, 3, 4, 5, 6, 7, 8, dot, 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 all the way up to 20. Those are our possible number of successes, correct? We're going to pretend that my dots go all the way to 20. I want these successes. These are the ones I'm looking for. I want the probability that we get something in that box. Every time we see the words at least, we use the complement rule. I want the probability that not this, right? I want the probability that not this. So I want the probability that X is not less than or equal to 3. Therefore, I will do 1 minus the probability X is less than or equal to 3. What this is going to look like. 1 minus binom, and it's CDF because it's a range, 20 trials, 0.35, 3. I'll show you how to put it in your calculator in just a minute. I'm going to let you write this down. I'm hoping that I say that enough times that every time you see the words at least, you use the complement rule. I hope by saying it enough times that it's just going to stick in your brain. Okay, let's jump to my calculator. There's a couple of different ways that we can do this. I can put the 1. I don't know why it's been doing that lately. Okay. I don't know where we lost me. I don't know where we lost me. I'm going to jump back though, because I don't know where we lost me. It's very strange how it just does that. I don't know what's going on. My internet, for some reason, I don't know if it's the internet, because it does it on both my computers. I get kicked off on both my computers, so I don't know if the internet's flickering or what, but okay, I'm going to jump back. Did you guys get this screen? Okay. So I'm going to jump back to my calculator. Yes, but. Yes, but. It froze before the red lines. Okay, I'm going to give you a second then. So every time you see the words at least, use the complement rule. That's kind of where I was saying. So we did, so we're looking for it to land in that purple box. So it's not 0, 1, 2, or 3. So we're looking for the probability that X is not less than or equal to 3. So therefore we do 1 minus the probability that X is less than or equal to 3. So what this is going to look like is 1 minus binom CDF with the 20, 0.35, and 3. I'm going to show you what that's going to look like on the calculator. Okay. So there's a couple of different ways you can do this. I usually put 1 minus in first. Give it a second because I see there's a delay.
Question. Sorry, can somebody hear me?
Yeah, I hear you.
So on a calculator, you put negative one negative binomial FDC, and then the
No, put 1 minus, not negative. Do 1
okay.
minus, and then you're going to do second vars and go down to binom CDF. And then we already have this in here because this was kind of the last one. Number of trials is 20. Probability is 0.35. And then our X value is 3 because we're doing not less than or equal to 3. And let's go down and paste it. You should be able to see what it looks like. So it's 1 minus that. This is one way to put it in the calculator. I'm going to show you the other way in just a second. And then I'm going to hit enter. So our probability that it is greater than that we get a number of successes greater than or equal to 4 is 0.9556. I'm going to show you the other way to do this. Yes, the binomial probability, we only use it with discrete random variables. Yes, it has to fit that criteria that we did on that first screen for 6.3. It has to fit that criteria. And it will be pretty specific. I'm going to make sure on the test that I tell you that it's a binomial experiment or use binomial probability or something. I'm going to make sure those trigger words are in there. I'll make sure that that's there. Okay. So I'm going to show you the other way to do this. We can just do this by going into second vars and do the binomial probability first. So I already have all my stuff in here and I got my value. Now you can do 1 minus, and notice how above this negative sign right here, it shows answer. I can do second, the negative sign, and it's going to grab the answer from before and it's going to calculate it. And I don't know if your calculator does it, but mine has a copy paste feature. I learned a couple of terms ago that not everybody's has that. But if yours has it, you're going to be fancy. You can, I'm going to do it again, 1 minus. If yours can copy and paste, use these little arrows on the circle, and I can arrow up and highlight this value. And then I hit enter once I highlight it, and it pastes it in for me. I use this frequently when I do typos because I typo a lot and I'll like paste it and then I can make changes. Because I can do that like here. Let's say I made a typo on my binom. Let's say that I wanted this to be 5 instead. I can paste it and then change it to a 5 if I wanted to. It's really cool. If yours doesn't copy and paste, don't worry. Still have a good fancy calculator. Questions on this before I move on? We're going to do a whole bunch of them together. Okay, we've got more examples. All right. Okay. Um, I would like you to try these. I'm going to work behind you. If now you might get stuck on D, stop at D, or you can, if you're brave, you can try D, but I haven't shown you how to do that one yet, so feel free to stop there. You should be able to do A, B, and C. And if you get stuck, that's okay also. I'm going to work quietly behind you. I would like you to give these a shot. Whew. Okay. All right, how we do? The important thing on the letter C, at least 3 means not x is not less than or equal to 2. So it's really important to think about what you're not including and thinking about that CDF is less than or equal to, not just less than. We do okay? I'm going to save D for a minute. Questions on A, B, or C before I move on to D? All right, let's take a look at D. So what we're looking for in D, and I'm going to write down numbers again, is 0, 1, 2, 3, 4, 5, 6, 7, 8. I'm not going to go all the way up to 20 because that's just ridiculous. What I'm looking for is this group right here. I want that group right there. Now, I don't have a function that gives me greater than, so these don't even matter. I don't have anything that gives me greater than. But what I do, all I have exact, and I have less than or equal to. So what I can do is I can do less than or equal to 7, and that's going to give me all of this. Less than or equal to 7 is going to give me all of this. Then what I can do is I can subtract off less than or equal to 4. So what I would do is it's going to say probability x is less than or equal to 7 minus the probability x is less than or equal to 4. That's what I would need to be doing here. So it's going to look like this. Twenty 0.417 minus, and I'm running out of room, binom CDF 20 0.414. Uh-oh, yeah. And then you can put that all in your calculator at one time. I'll show you. I'm going to give you a second to write that down. And then we'll put the whole thing in the calculator at once. I'll show you what it looks like. Okay, pop over to the calculator. I clear everything out because I don't like a cluttered screen. So do second vars. Go down to binom CDF. We have 20 trials. My probability that they are a wireless only household is 41, which I think it's probably a lot higher than that these days. And then 7, because we want 7 or less. And just leave it here. You don't hit enter and hit the minus button. And go in there again. Binom CDF 20, 41, and 4, because I'm subtracting that off. So all of that is in there. You're more than welcome to do them separate and then subtract them. I just like putting it all in at once. So my probability here is about 33.8%. Questions on that?
You subtract binomial? Is that what it means? Minus binomial?
Yeah, I subtracted just like I did like I wrote it down here. I did binomial CDF 2041.7 minus binom CDF 2041.4. So I subtracted off the 4 or fewer. So you did binom CDF twice.
Oh, so what you did is basically you took that like first group and took the first of that group, the highest of that group, and then subtracted by 7.
Right. So, well, so the
4
first,
times 7, that's what I noted.
okay, so this right here gave me 7 or fewer. So it included this piece that we don't want. So this is that piece we don't want. I subtracted it off.
Oh, okay. So you just subtract two groups. From
Right.
one of them. Okay.
Yeah. Perfect. Other questions? Okay. I'm going to move on to mean and standard deviation of binomial random variables. So the problems that we use with the mean and the standard deviation of the binomial random variables, sometimes I like to do them a little differently than our textbook likes to do them, but I'm going to show you both ways. But the textbook likes to overcomplicate things sometimes. So I'm going to show you like simplified way because not very long ago we talked about what makes something unusual. And we actually talked about it on like last unit, or I don't remember if it was chapter 5, it might have been. Anything that occurs less than 5% of the time is considered unusual. Remember that conversation? So that stays with us. We do not leave that at the door. That came into chapter 6 with us and is so helpful. Anything that occurs less than 5% of the time is considered unusual. So we're going to use that information rather than using a two standard deviation rule or using z-scores. We don't care about all that right now. Anything that occurs less than 5% of the time is considered unusual, and we're going to hold on to that for dear life because it makes our life easier. So the expected value of a binomial random variable is super easy. You take the number of trials and multiply it by the probability. So just that's what our mean is for a binomial random variable or expected value. Mean and expected value mean the exact same thing here. So for standard deviation, you take the mean or the number of trials times the probability of success times the probability of failure, and then you take the square root of the whole thing. So number of trials, probability of success times the probability of failure, and then take the square root. That's how we calculate the standard deviation of a binomial random variable. Okay. So let's calculate it here. So according to Experian Automotive, 35% of all car owning households have three or more cars. We have a simple random sample of 400 car owning households. We want to know our mean and our standard deviation. So super simple. My mean would just be the 400 times 0.35. This tells us how many we would expect. So 400 times 0.35. So out of the 400 households, you would expect 140 of them to have three or more cars. That's what we would expect. That's what that expected value means in this case, that out of 400, you would expect 140 of them. This is actually math that you've done before. We just didn't call it expected value. Standard deviation, slightly different. Take 400 times the probability of success times the probability of failure. You can put that whole thing in your calculator at the same time, as long as you are careful with parentheses. You can put the whole thing in there at once if you're careful with parentheses. Or you can do 400 times 0.35 times 0.65 and take the square root of that. But just be really careful with your parentheses. About 4.77-ish. And the standard deviation means the same thing here. So if I went two standard deviations above 140 and two standard deviations below 140, I would expect 95% of all samples of size 400 to be within those two numbers. If that makes sense. Every sample size of 400, I would expect, I'm going to pretend 4.77 is 5 just for the sake of argument. I would expect, if I took a whole bunch of samples of size 400, I would expect 95% of them to have between 130 and 150 people that have three or more cars. If that's what the standard deviation is saying here, is that I can use that empirical rule here to kind of say 95% of the household of the samples are going to have this many people with three or more cars. That makes sense? Okay. So this is important. This is a rule of thumb. I'm not doing quizzes in this class, but it's possible that on your test it would ask this. How do we know that it is bell-shaped? How would we know that it is shaped normal? How would I know that I have a pretty bell-shaped? This right here. If I take NP times 1 minus P, which is that piece underneath the radical and the standard deviation, if I take that, if that number is greater than or equal to 10, then it's approximately a bell-shaped distribution. It's not skewed right or left. It's a nice, pretty bell. This is
So
our,
if it's 11, it's not a bell anymore. So it has
no,
to
it
be
is.
like
It just has to be greater than 10. If it's 9, it's probably skewed.
okay. So
But
above 10, above
above
10.
10, right? And
Okay.
this is, there's a, and I don't remember if it's chapter, I don't remember if it's this chapter or if it's the next chapter, but it's, if it asks you to describe your distribution, this is one thing you check. I think it's the next chapter though. But if it asks you to describe your distribution, you're going to say it's bell-shaped. If you're going to check NP times 1 minus P if it's greater than or equal to 10, that means that your sample size is large enough that I have enough successes and failures there to make it bell-shaped. So, and I don't think it asks you that in this unit. I think it asks you later, but I can't remember. It all kind of runs together for me. All right. Empirical rule. We remember 95% of all of our observations are within 2 standard deviations of the mean, which means anything that occurs less than 5% of the time is considered an outlier. It is considered unusual. Unusual happens less than 5% of the time. If we get a probability that's less than 5%, it's considered unusual. And usually, if it's unusual, like if we took a sample and our number of successes is unusual, then either the original probability is wrong or there was some other factor at play here. So if I, like, for example, back here, if I took a sample of 400 cars or 400 households, and I ended up with 185 of them that had three or more cars. I would either have to say, because that would be unusual, it'd be more than 2 standard deviations from the mean. I would have to say either my 35% probability is wrong, or maybe I had a large number of like wealthy neighborhoods, people that are car collectors. Maybe, maybe my sample wasn't really random and I took it out of an area that has, I don't know, a lot of people that can own a lot of cars. Who knows? There might be some other factor at play there. So generally, when you get an unusual answer, you start questioning things. Why is it unusual? Why did I get that? What's wrong with my data here? That's usually what you do. And I'm probably giving you way more information than you need, but I'm trying to make this useful for outside of this class rather than just having you pass a test. Okay. And we already got these. How come I got 9.54? What did I do wrong here? How did I math wrong? Hmm. Oh, I put in 100 instead of 400. My number was wrong. I typoed. Here's the correct answer. I typoed in my calculator. It should be 9.54, not 4.76. I put 100 instead of 400 in my calculator. I apologize. See, another
So,
example. Your math teacher's human.
so right now the way that the formulas are correct now. The
The
ones that
formulas were correct. I just typoed in my calculator.
oh, okay, you have that. Okay.
Yeah. So what we want to know now is this person, somebody conducted a simple random sample of 400 car owning households. They found that 162 of the households had 3 or more cars. We want to know, is this result unusual? There's a couple of different ways that you can do this. You can do binomial. Um, you can use the binom PDF to see if that would be unusual. Or you could determine if it's more than 2 standard deviations away from the mean. Now, since I have the mean and the standard deviation right here, I'm just going to use the 2 standard deviation rule. So let's take a look. 140 plus 2 times 9.54. Let's see what that is. Uh, That number, that right there is 2 standard deviations above my mean. 162 is higher than 159.08. Therefore, 162 is unusual. See, 435. When I put it into my calculator, I did binom PDF because he got exactly 162, 400, 0.35, 162, and I got 0.003. That is less than 5%. Therefore, it is unusual. Either way works fine. Now, if they are not making me calculate the mean and the standard deviation first, I'm just going to use binom PDF. Because that's faster, right? But they already made us calculate the mean and the standard deviation, so we might as well use it. But if they don't make you, just throw binom PDF in your calculator and go with it. Does that make sense? So both ways. Now, maybe you're not sure. You can check both of them. Why not? This is backup, right? You can check it both ways and see which one works. I would like you to try this one. You can, well, first go ahead and calculate the mean and the standard deviation. I'm going to give you a moment to calculate those. So we're looking at the wireless only households. It's 41%. Our wireless only, that was our percent. In a simple random sample, 300 households, 143 were wireless only. Is this result unusual? Remember, they say that 41% of all households are wireless only. So go ahead and calculate that mean and standard deviation. I'm going to work quietly behind you.
Okay, how did that end up being 0.41? Oh, you rounded.
No,
Okay.
it's 41% turned into a decimal is 0.41.
Okay, if I were to read this and I say 300 households, 143 were wireless, how did you
Not
do
even
it?
we haven't even used the 143 yet. We're
Okay.
just calculating the mean and the standard deviation right now.
Is there a place where it shows 0.41 or did we borrow it from another
That
place?
was it says we're looking back at the wireless only households problem, and
Oh,
that
okay.
problem
We're
was
looking back, okay, to another, okay.
yes, yes, yes.
That's why I was thinking it was abstract a bit, but now I understand. Okay.
Yes. No worries. Okay. So how did we do on the mean and the standard deviation? I don't think I typoed this time. Did we get the same thing? So now you're going to determine if it's unusual, whichever method you want to use, but we already have the mean and the standard deviation, so we might as well go with it, right? Hmm. Okay, so that would make this unusual though, right? Not unusual because we're looking at 143. We got a household with 143. Yes, it is unusual because 143 is greater. And once again, I got 0.003 as my with my binom. So if you use binom, you would do binom PDF. We're using PDF because it is precise. It is exactly 143. We're wireless only. So I did 300.41, 143. I used the precise 0.003. That is less than 5%. Therefore, it is unusual. It would be unusual. Now, sometimes if things are just like slightly unusual, like if I would have gotten if I would have had like 4.8% or something, sometimes we'll just be like, okay, that's close enough. We're going to call it good. But something like this would really make me think, you know what? That's less than 1%. So there's probably something not right here. There's probably either 41% is not correct. And I'm going to show you we're going to do hypothesis testing later on where we say, I think that it is different now. I think that it's probably more. Like at this case, I would say, this study shows that 41% of all households are wireless only, but I think that number is greater than that today. And I'm going to show you how to test that because I could pretty much guarantee that that number's higher now than it was back when whatever this study was done. I mean, my guess is we're probably in the 70 to 80% wireless only households. That's my guess. I don't know. That's just a guess here, but definitely not 41% anymore. And I think it's for sure more than 50. All right, any questions on that?
We're good.
Okay. So, biggest thing takeaway tonight, remember, anytime you see the words at least, use the complement rule every single time. I know that I'm saying that and it's like you guys, class, just stop. Just stop it. But seriously, I want that in your brain so whenever you run across the words at least, you use the complement rule. So any questions on like while we're still on the recording? This is my last slide. So any questions?
So whenever we say compliment, it means you clap, or should you refer to
It's the
a
one
formula?
minus. It's the one minus. Every time you
Oh,
see the words at least, one minus.
can you put like one minus and put complement rule? Remember, because that would help me so much with like knowing like a visual connection. If you put like minus one minus whatever that, so it
We
could.
have that on a different, so it's one minus P is the complement rule.
Oh,
So
thank you so much.
every time you see the words at least, use the complement rule every single time.
And can you put like at least like in parentheses on top of
Yeah.
that just to like tie the two concepts together? Yeah.
I think on Thursday I like wrote it really big across one of the pages, like every time you see the words at least use the complement rule. Pretty sure I did that on Thursday. But make sure you're doing that. Make sure that every time, and of course it's up where you can't see it. Every time you see the words at least use the complement rule every single time. And I'm gonna flip to the next page. So remember, binom PDF precise. Exactly. Exact, exact number of successes. And then binom CDF, cumulative, This is a range of successes. There we go. So hopefully that got us everything we need. You should have enough to do the homework, all of chapter 6. We're going to do all of chapter 7 on Thursday. And then next week, Tuesday, will be office hours again.
Thank you very much. Thank you.
I'm going to turn off the recording.